Okay, so there we are. Excellent. Okay, so for today's lesson, we are going to continue finding derivatives using first principles. Okay, today we're going to kind of explore when a function is differentiable or not. Okay, remember from last day that for a function to be differentiable, the function must exist and the function of the derivative must also exist. Okay, today we're going to get into some instances where we're actually not going to be able to find the derivative because the graph is not, I don't know, there's some sharp turns and curves in the graphs, so we won't be able to find the derivative at that point. In these cases, the left-hand limits and the right-hand limits are not going to be equal. So this is going to tie in a little bit with our limits, and we're going to do some proofs with left-hand and right-hand limits too, okay? Are there any questions before we get going? Perfect. Okay, so with first principles, so we have two functions here. So we have a f of x is equal to x squared minus 4, and we have a g of x, which is the absolute value of x squared minus 4, okay? So if we were to, let's start with this guy here. So we will graph that one. So x squared minus 4, we know we'll have zeros at -2 and 2. And also with a y-intercept of -4. So our graph is going to look something like this. Okay, so that's easy enough. Now let's shift to the one on the right where we're looking at our g of x function. So this is the absolute value of x squared minus 4. So in this case, all of the negative values are going to be positive instead, okay? So it's going to look similar to this graph, but all the negative values, so anything that is below the x-axis will be reflected above that x-axis, okay? So we still have our -2 and +2 points. It's gonna be our +4 now, and then our function will look something like this. Okay, and again, with the absolute value sign, all of the negative values will be positive now, okay? So now if we're gonna find the derivative of each, just gonna split piece of paper in half. All right, so, and we're still using first principles here. So the derivative, so f prime of x, that's just saying that we're finding the derivative of f of x as equal to the limit as h approaches 0 of f of x plus h minus f of x over h. Okay, so every time that we see x plus h, x, we will substitute in x plus h. And then for f of x, we will substitute in f of x for each time that we see x, like we've been doing, right? So let's go ahead and do that. So f prime of x is equal to the limit as h approaches 0 of x plus h squared minus 4 minus f of x we can just put an x there because f of x is just going to be squared, so we'll have x squared minus 4 in brackets, that's all over h. Now we can simplify this. So we will have, if we expand this, we'll have x squared plus 2xh plus h squared minus 4. that negative will be distributed in there. So negative x squared, negative multiplied by -4 will be +4 all over h. So we can clean this up. So x squared and a negative x squared, we have a +4 and a -4. So if we just clean that up, we'll have 2xh plus h squared over h. We will factor out h. We'll have 2x plus h over h. These h's will cancel. 2x plus h. Now that we are fully simplified, we can substitute in our h is equal to 0. So our f prime of x, or our derivative of f of x, is equal to 2x. Okay, so that's the long way to do that. And this f prime of x here, because it's 2x, therefore f of x can be differentiated for all real values of x. All right, so that's using the first principles strategy. Remember last day I talked about the chain rule and saying that's going to help us find the derivative quickly. I mispronounced it. It's actually the power rule. The chain rule is also a rule, but don't worry about that. And if we did that, so we'll just take the exponent on the variable, put it out in front, and then subtract 1 from here, right? So if we do that, we'll have 2x to x to the 1. So we'll just have 2x down here, okay? And again, we will learn about that when we return from the break. Okay, so let's try to find the derivative of g of x now. So the derivative of g of x would be g prime of x. And that's going to be limit as h approaches 0 of g of x plus h instead, minus g of x over h. So same thing, we will substitute in x plus h for every time that we see x squared. And then we will substitute in g of x for each time that we see x in this one. So, and remember this one, we're doing the absolute value. So let's not forget our absolute value lines. So we got x plus h squared minus 4, absolute value, minus g of x in there would just be x squared minus 4 divided by h. Okay, we can expand this. So then we will get x squared plus 2xh plus h squared minus 4. That is all in absolute values. Subtract x squared minus 4 over h. Now, at this point here, we cannot actually simplify any further. So I'm just going to write a note here, right? Because we don't know information regarding the absolute value, if it's positive or negative, okay? So that's as far as we can go in this case. This is as far as this can be simplified. Without knowing more information regarding whether absolute value is positive or negative. Okay. So this will lead into the next sheet of paper here. So since g of x is not differentiable for all real values of x, because we cannot simplify this further, kind of like what we have found down here. So yeah, so we say it's not differentiable for all real values of x. Okay, so let's jump into the next page here. So since g of x is not differentiable for all real values of x, let's try taking the derivative at x is equal to 2. So we need to find the g of 2. Okay, and this question here, we're going to find the left-hand limit and the right-hand limit. So we're doing the left-hand limit and the right-hand limit separately, because in order to determine specific values, we need to know whether absolute values are positive or negative. So this is where we need to find the left-hand and right-hand limits separately. If our left-hand limit does not equal the right-hand limit, so the limit will not exist, and also our derivative will not exist for that value of x. Okay, so we'll find g prime of 2. Okay, so that will be, we'll substitute 2 into this formula up here. Okay, so g prime of 2 is equal to the limit as h approaches 0 from the left, so 0 negative, of 2 squared plus 2 times 2h plus h squared minus 4. I'm running out of space here. Oops. Minus absolute value of 2 squared minus 4. And that is all going to be divided by h. So we can simplify this. I'm just going to move over a little bit. So limit as h approaches 0 from the left. 2 squared is 4 plus 4h plus h squared minus 4. Don't forget our absolute values. Subtract absolute value of 4, 2 squared, and then minus 4 all over h. Okay, so we can clean this up a little bit. We have positive 4 and negative 4, and 4 minus 4 is equal to 0. So we'll rewrite this. So 4h plus h squared, an absolute, minus the absolute value of 0 over h. So I'm just going to rewrite this here. So I'll have limit of 4h plus h squared over h. Here we can factor because we have h's in both. Okay. So one more thing I'm going to do. So limit as h approaches 0 minus. We can rewrite this as absolute value of h multiplied by the absolute value of h plus 4. over h. So we can split this. So I'm just going to show the proof here. So absolute value of a number multiplied by another number is equal to a positive. So this case here, we can split this because this, so right here, will provide the same answer. So if we have like a number multiplied, the absolute value of a number multiplied by the absolute value of a number is equal to positive multiplied by a positive, which is equal to a positive. Okay. So here, we're kind of happy with this guy here. We've split this up. It's moderately simplified. So in this case, we have x2 and x1. X. And here, since we are approaching from the left.
Wait, what? How did you get x1 and x2?
Okay, so in this case, because we are like, so in this case, it's just like a general graph here, okay? So I'm just showing you why we're going to have a negative h here, okay? Because we are approaching from the left, our h should be negative, right? Because h is the change between two x values. So in here, if we have h, remember, h is the distance between two x values. But if we're doing x2 minus x1, so if we're going to the left, our h should be negative here. So remember, anytime that we're going to the right, so anytime that we're finding like x1, in this case, so if we're finding the point that's more right than the point that's on the left, we should expect to have a positive h, right? Because that would be the distance from here to there. But in this case, as we're approaching from the left, we're going to be doing x2 minus x1. So we should have a negative h there. Did that answer your question there, Quinn?
Yes. So x1 and x2 are just kind of arbitrary, like mark them down on the graph. They can be what you want them to be.
Pretty much, yes.
Okay.
This is just like the proof here saying that we're going to have a negative h because we're approaching from the left.
Okay, got it.
Okay, great. So yeah, so negative h, x2 is to the left of x1. So anyways, I'm just going to finish this out. So since we are approaching from the left, we know h is negative. Good questions. Good questions. Okay, I just need to grab a sheet of paper, so give me 2 seconds. Okay. So in summary, so taking that into consideration, the limit as h approaches 0 negative will be negative h multiplied by h plus 4 over h. These h's will cancel. we'll be left with negative absolute value of h plus 4. Now that this is as simplified as we can get, now we can substitute in our h for 0. Negative 0 plus 4. 0 plus 4 is just 4. So we will get negative 4 for our answer. So what did we just find here? So we found g prime of 2. So we found the slope of g of x at x is equal to 2. So if we jump back to our first graph here, so if we look at x is equal to 2, which is right here, does our slope of negative 4 look reasonable as we approach from the left? So remember, if it has the slope of 4, it would be decreasing by 4 units as it moves over 1. So as we approach 2, I think that is a reasonable slope.
Mr. Jones,
Yes.
how come only the first h is negative and all the other ones are still positive?
How come the first h is positive?
Like,
Yeah, no, I understand what you're talking about. So if we were going to, so saying that it's a negative h. Oh, Aaron, that is a really good question. Can I look into that and get back to you?
yep, sounds good.
Okay. Okay. I will look into that. Sorry, I can't answer it right now. I apologize. Okay, so just in summary, so looking at the graph, does minus 4. Does minus 4 seem like a reasonable slope for a tangent as we approach x is equal to 2 from the left? I think it is. I think that looks reasonable as we approach from the left. Okay, so let's jump back to our right-hand limit here. So we should expect our h to be positive here, right? As normal, we're approaching from the right. So the right-hand limit, so g prime of 2, bragging around with space already, as h approaches 0 positive. So I'm just going to go down here. So absolute value of 2 squared plus 2 times 2h plus h squared minus 4 minus 2 squared minus 4. Over h. So I'm just going to save a step here. So 2 squared is 4 minus 4, so those we can get rid of. And 2 squared minus 4, that is going to equal 0 there. So limit h approaches 0 from the right of absolute value. So we'll have 4h plus h squared minus 0 over h. Okay, so like we did over here, we can rewrite this because it will still give us the same positive answer. So we'll have absolute value of h multiplied by h plus 4. That is just this expanded a little bit over h. Okay, and because we are approaching from the right here, so if we have x1 and x2, our h will be positive. Okay, so that'll be handy for us. So limit as h approaches 0 from the positive of h plus 4 over h. These will cancel. Okay, and now at this point we can substitute in our 0. So 0 plus 4 is equal to 4. Okay, so this is the slope of our function g of x at x is equal to 2. If it is equal to 4, positive 4, so we should expect it to be going up 4 units as it moves over 1. Okay, so I think that is a reasonable slope for that. So in summary, so at x equals 2, what can we say about the left-hand limit and the right-hand limit? Well, the limit does not exist because the limits do not match one another. Okay, so at x equal 2, left-hand limit does not equal the right-hand limit. So the derivative does not exist. So therefore, this function is not differentiable at x equals 2. And by the way, this is the long way. Okay, so as we go through the next couple examples, it's not going to be as long. Okay, I just had to show you guys how to do that algebraically, but now in these next couple examples, we can just kind of use our brains. Are there any questions so far before we go ahead? All right.
So we just solved for the derivative, and the derivative is the limit?
Okay, so we just found the derivative.
Okay.
Right, okay, so in general, when we find the derivative, that will tell us the slope of the function that we're given in general. Okay, in this question, we were finding the slope at a particular point, so at x equals 2. So that's when we're going to be substituting in x is equal to into our derivative or our general slope formula for that function. Is what we just did, we were checking if the left-hand limit and the right-hand limit, if they were equal to one another.
Okay. So
what we are going to learn is that if the left-hand limit and the right-hand limit do not match, if the limit does not exist, then we will not be able to differentiate the function at that particular location.
Okay, so what number on our page is the limit?
What number on the page is our limit? What do you mean by that? Like what we just solved?
Well, like when you look at the graph,
Mhm.
like it kind of looks like the limit would exist because the right side and the left hand side like look like they come together at the same point. But like if like what numbers on here like led us to believe that the left hand limit and the right hand limit don't exist? Sorry if that makes sense.
No, that totally makes sense. So when we solved algebraically from first principles here, like right here, we found that the left-hand limit to be -4 here. Okay, and it was negative because as we're approaching it from the left, from 0 negative, that's when we're assuming that h is going to be negative as well. Only the first h. I will figure out why the remaining h's are not negative. Okay, but because that the left-hand limit and the right-hand limit did not equal one another, then the function is not differentiable.
Okay, so then it's like the limit is like the slope then?
The limit is the slope. Yes.
Okay.
Yeah. So when we look at these next three examples, it might help clear up some of your questions regarding this stuff, okay? But really good questions. Okay, so let's get into some shortcuts for us so we don't have to do that every time. So key idea, so a function is not differentiable at x is equal to a, so a being just like a general point, if there is a sharp transition in the graph at x equals a. So for example, if this is point a here, if the function went in like this, we cannot find the derivative or the tangent of the slope. Okay, so and the reason for that is that at a we could have tangent lines going in many different directions. Okay, and like we just calculated, like the slope as we were approaching a from the left, it was a -4, right? But then as we were approaching it from the right, it was +4. So if we were trying to find like the slope of the tangent line, which slope would we decide to use, right? So that's why we are not able to differentiate at that particular point. So a tangent at x equals a cannot be determined therefore f prime of a does not exist. So just another note of that, we cannot definitively say at which rate f of x is changing at this particular point, because we don't know if it's going up or if it's going down or if it's going flat. Okay, so if there's sharp transitions in the graph, we consider that region of the function to be differentiable, undifferentiable, or not differentiable. Okay, number 2, when the tangent is vertical at x is equal to a, we also cannot find the slope of the vertical tangent. Okay, so if we have a function here, kind of looks like that. So the vertical tangent at x equals a. So the slope of a vertical line is whatever number it is rising at over the run, which is 0. So that will give us a defined answer, undefined. So right here. So therefore, f prime of a does not exist. Okay, and lastly, function is not differentiable at x is equal to a if the function is discontinuous at x is equal to a. So whether there be a point of discontinuity, section of the graph that does not exist, or the limit at x is equal to a is not equal to the function of a. Okay, so if the function at a point does not exist, then we cannot find the derivative. So f prime of a in this case at that point. The derivative describes the graph, and in this case, if a point does not exist, the graph does not exist or is not continuous. Okay, so derivative describes the graph. In this case, like if the function is discontinuous, or it's not continuous, therefore f prime of a does not exist. Does that make a little bit more sense from the last topic there?
Yeah, it does.
Great. Okay, so let's apply these 3 ideas to the last page here. So we are given a fun-looking function. Okay, so let's go from left to right. So this can be 0.1. It can be 0.2. 0.3. 1.4. This can be 0.3 here. Don't want to forget. So this is 2. This is 3. 1, 2, 3, 4, 5, 6. So at 1, so x is equal to -2. So is this going to be differentiable at x is equal to -2? Well, if we go any further left, if we get more negative than -2, the function will not exist. So this is not differentiable at 0.2. So differentiable. I can't spell it now. There we go. Differentiable at, so at x equals to 2, -2, the function does not exist for x is less than -2. And the left-hand limit does not exist. Okay, so at 0.2, so our 0.2 here will be at x is equal to 2. So I hope you can see there's a little dot at x is equal to 2. So at this point, we have a point of discontinuity. So the function at x equals 2. So f of 2 is discontinuous. Therefore, f prime of 2 does not exist. Okay, we'll just continue. So at 0.3, so right here, x is equal to 3. And in this case, we have a sharp transition in our graph. Okay, moving on. 0.4 is where x is equal to 5. So same thing. There is a sharp transition in the curve. At 0.5, so up here, x is equal to 8.5. And in this case, the tangent line is vertical. Therefore, slope is undefined. And lastly, at 0.6, x is equal to 10. So this function, like we had over here, it's not defined for any values where x is greater than 10. Okay, so the right hand. Okay, so to summarize today's lesson, so discontinuity and continuity. So when we have a function that, just pulling up, so if there is a sharp transition in the graph, or if we have a vertical tangent line, or if there is a point of discontinuity, these three cases individually will make that function undifferentiatable at that particular location. Okay.